In this video, I will show how to implement the math theory in the modeling of the Revit family that correspond with one phase or our D-box family that we are developing. So, in order to begin, I have to say that this process of understanding the theory of this family is very crucial because this is a pretty complex family, and actually handling the relationship between its parameters is going to be crucial. As you can see here, these are the parameters of this family. This is only one of four phases of the family, of the D-box family. So each phase will have these parameters and will have variations, slight variations in these parameters in order to implement correctly the math theory. Actually, it is a mathematical theory that is very simple. It's only an application of the Pythagoras theorem. So it won't be complicated. But the relationship between the parameters can be quite complex. And I want you to really understand it because it's going to be a challenge. So, first of all, I will move this parameter. So I haven't defined this yet, but I will do this to help you to see better the information. This must go in constraints. Okay, perfect. So each of these Revit family that are called phases will have this set of parameters. I organized the parameters in constraints, dimensions, analytical alignment, data, and other. This is very important because each of these parameters are necessary. Well, there are only a couple of parameters that are analytical parameters, but actually they are good for evaluating if we are doing well the calculations. So the first three parameters are the parameters that define the angle, the elevation. This is a default parameter of a Revit family, and the width. Actually, these are the only parameters that the architect or the engineer or the user in general is going to touch. The parameters of this phase that will be included in the D-box family that are going to be handled by the architect are these couple of parameters: the angle parameter, the width parameter, and the default elevation. Actually, default elevation shouldn't be handled by the user. So how does this work? I'm going to continue my explanation. The theory behind the family is pretty simple. We have a family. I will draw it over here so you can understand it better. Let me put my board over here. Okay. And let's draw it over here. Here I want to see this part of the screen. Perfect. And I want to use some color. Okay, one red. Yeah. So the theory behind the family is this. We have two sides that are going to control the corners. These are the corners. We have one side and another side. This part of the family is necessary because when we have two faces that has angles, we need to match the angle of the right face, for example, and the angle of the front face. This is the main body of the D-box. So we need to solve this encounter between two faces. here you can see, here you could say, why don't you start the angle right in the corner? And the answer is because you then delete this line and you cannot construct back the family. So you will always need this line, and you will say, why do you need that line? And the answer is because if you are going to draw the angle in the opposite direction, that is to say in this manner, as you can see here in the board, you need to stretch this side, so you cannot lose this line. So you need to keep it, and in order to keep it, you cannot make its length 0. So you will need a corner here to solve this problem. I made a mess here in this drawing. I'm going to use another color so I can explain it. Yeah, here some, I'm sorry, here some blue. Okay, here it is. You need to define this corner. So this will be a corner family, and this can be optional for the family to work. So let's continue. So that's why we have the main body of the T-box. This is the main body. This will control the width and the length of the family. But the first thing that we have in each face is a corner distance. This is the corner. And this corner is independent of it in each side. You have a left corner, and here you have a right corner. A right corner. Why? Because here you can have an angle in this manner, and here you could have an angle in this manner. So if you have this angle in your front face, that is our current analysis face, you will need to create an angle in this manner, the left side, and another corner in this manner, so you can extend this angle over here. So as you can see, we really need this couple of corner parts in the family. And the next thing that I want you to evaluate is, but actually let's stop here. The video is getting quite long, so I would like to leave the other parts of the analysis in a separate video, but consider that we have this couple of elements called corner distances. The right corner and the left corner are independent and resolve the encounter between the angle of the faces. And one last thing that I'm going to consider in this corner family video is the fact that when we calculate the angle of this face, when we calculate this angle over here, we really need to take in account this corner, because we are going to calculate the angle with an imaginary right triangle, right? We're going to calculate it with an imaginary right triangle. But when we calculate the distance, we're going to have to sum the opposite side of the angle, that is this one, the opposite side, this distance. We're going to have to sum that opposite side with the corner, in this case the right corner. So keep this in mind. You will have to include this in your Revit formulas in order to make this family work. So in the next video we will start actually calculating this triangle, and we are going to start seeing how this is incorporated in the Revit family parameters.